Hello student, myself Mittal Roy in the Department of Electronics and Communication Engineering in GEM-Tech, Greater Noida. Today I'm here to give you next video on Analog Electronics 1, and the topic of my video is today's topic is bias and stabilization. Need for biasing and stabilization. In the previous videos, I have given you the review on basic semiconductor electronics, diodes and BJT. Now we will enter into the topic with the need for biasing and stabilization. So basically, what is transistor biasing? Basically, in order to operate the transistor, we have to apply some voltage, some DC bias, and that voltage must be applied in an appropriate manner. The appropriate manner means the polarity, the magnitude and a particular values of the voltages should be proper, should be perfect in order to get the desired results out of our device, which is the transistor. So there is a need of proper transistor biasing, which is termed as transistor biasing. The DC voltages are used to bias the transistor. See, both DC and AC are required for transistors to work. DC is something essential. It is like the breath, you can say. Nobody can live without breathing. So DC bias is like providing breath to the device, and AC is something which we apply and accordingly we get something out of it. Like for amplification, we apply small AC and get a relatively large AC. So DC is the basic need, basic requirement of a transistor device. Now, the operating point of the transistor. Basically, the operating point is also called as the Q point or quiescent point of the transistor, and it lies at the VI characteristics of our output VI characteristics of common emitter amplifier, where the VI characteristic meets the DC load line. The cutting point of the DC load line and VI characteristics brings us the required operating point. Now, need for biasing. To operate the transistor in the desired region, the DC sources supplies the power to the transistor circuit to get the output signal power greater than the input signal power. So this is the requirement of a transistor. Now the load line. It is the straight line drawn on the characteristic curve. I'll show you the characteristic curves in this video, where the DC load line is a straight line that is plotted on the VI characteristic curve of a transistor. It is used to fix the operating point of a transistor. There are two types of DC load lines, AC and DC. This is the graphical representation of a load line. See, this particular line going from B to A, this is called as our DC load line or load line. It is drawn on the VI characteristic plot taken between output voltage VCE and output current IC. And this is the output VI characteristic of a transistor in common emitter mode. There are three regions in this output VI characteristic. The region near x-axis is called saturation region. The region near y-axis, at x-axis the region is called cutoff axis. At y-axis the region is called saturation region. And in the middle, this region is called the active region. Okay, now the DC load line consideration. So we have to first consider an amplifier and we have to determine the DC load line. So first of all, from the given amplifier, we will be removing AC circuit, AC path, step 1. And it will be looking like this. Then we will draw the output DC load line. And to draw that line, we will apply KVL in this output port. The KVL is like minus VCC plus ICRC plus VCE equal to 0. Okay, after this equation, we will put this equation in the form of a straight line equation, which is y equal to mx plus c. Here y is current and x is the voltage VCE. So after putting that equation 1 in the form of equation 2, we get IC equal to minus VCE upon RC plus VCC upon RC. Now to find the coordinates of the load line, at x-axis y equal to 0 and at y-axis x equal to 0. Therefore we get VCE equal to VCC and IC equal to VCC upon RC. So finally we plot the line and we select the curve so that the Q point is obtained. Now applying KVL in the input port. This is our circuit. Let me show you the circuit again. Yes, in this circuit, if we apply the KVL at input port, it will be like VCC equal to IBRB plus VBE. If we consider it to be made up of silicon, then VBE is taken as 0.7 volt. So I have taken VBE equal to 0.7 volt, and from this KVL equation we will determine IB equal to VCC minus VBE upon RB. Okay, now we have taken an example that if IB equal to 3 milliampere, VCC equal to 20 volt and RB equal to 5 kilo ohms, then we have to determine the DC load line. And from the above equations mentioned, for DC load line to draw, we have to find the two equations. First is that VCE equal to VCC and IC equal to VCC by RC. These are the coordinates of load line. And the other equation is, in terms of IB, it is VCC minus VBE upon RB. So if we put VBE equal to 0.7, or ideally we can assume that if VBE equal to 0 in case of an ideal transistor, ideal PN junction. Now VCE equal to VCC, which is given to us as 20 volt. So this is 20 volt. To draw the IC value, IC equal to VCC by RC, and we have VBE, IB equal to VCC by RB. Okay, so we have IB, we have VCC. We can determine the value of RB from here, and with the RB is given to us, IB is given to us, so we can determine IB and RB are given to us. We can determine IC equal to beta times IB. So IC equal to VCC by RC. From that value, IC is equal to VCC given to 20 volt upon RC. So this is the conclusion, that the intersection of DC load line and curve is called as Q point. Now we have to select the operating point. There are three regions. One is near saturation region, near cutoff region, and the other is the active region. So there are three regions, out of which one is the best region that we have to select. So if in case of a near to saturation region, the biasing circuit is designed to fix the Q point very near to saturation region, and the collector current is applied to positive half cycle. Thus clipped, rather the collector current gets clipped, because near the saturation region, the y-axis, at near y-axis the current gets clipped. Because of this distortion present at the collector current, point P is not the suitable operating point. So if we take the operating point near saturation region, the current gets clipped. So this is the output curve. If we have taken it near y-axis, this is the y-axis, and because of this, the output current on the peak side and on the positive peak side is getting clipped. So this is not the appropriate region of biasing or taking Q point. Now if we take the Q point near cutoff region is near x-axis. So if the biasing circuit is designed to fix the Q point near cutoff region, the collector current is clipped at negative half cycle. So here the clipping will be observed in negative half portion of the cycle, and therefore it is also not suitable for biasing. And this is the output. So output, the current is clipped closely in the negative half cycle, in the negative half peak. This is the part of the clipped region. So here also, because this collector, the lower part comes in the cutoff region, and the upper part was coming in the saturation region. So if we take the operating point near saturation region, the upper portion will be clipped. If we take the operating point near cutoff region, lower portion will be clipped. Now the final third region is the active region. If we take the Q point at the center of the active region, the output signal is sinusoidal waveform without any distortion. So there will be a perfect sinusoidal output voltage, something like this. So for complete input cycle, we have a full output cycle. So it is a rough sketch. So therefore we can assume that out of the three regions, the best region for taking Q point is the active region. Okay, then comes bias stabilization. The point we have concluded is that the biasing point, the Q point, must be at the middle of the load line, exactly at the center of the load line in the active region. Now the question comes is that there are few factors, depending on them the Q point shifts from its center, from its original position, and these factors are like temperature factor, leakage current, VBE, which is doping factor, and transistor parameter like beta or HFE. So these are the factors, depending on them the Q point may shift. Let us consider each factor in detail one by one. Firstly, I am taking the Ico leakage current. The flow of current in the circuit produces heat at the junction. So since the minority carriers are temperature dependent, the leakage current gets doubled for every 10 degrees Celsius rise in temperature. So IC increases, hence the Q point shifts. So if IC increases, ICO changes, and when ICO changes, Q point shifts. Then VBE. VBE changes with temperature at the rate of 2.5 millivolt per second. And IB depends on VBE, since beta equal to IC upon IB. Therefore, increase in IC also changes the Q point. So every time we are getting a conclusion that the IC is changing, and this change in IC causes change in the shifting of the Q point, because the coordinates of the Q points are VCE and VCC by RC, which is the value of IC. Now current gain beta. The transistor parameters among different units of same type, same number changes. That is, if we take two transistor units of the same type and we them in the circuit, there is a change in the value of the actual practice. So the biasing is designed according to the required value, since the changes in operating point. So since beta changes, the operating point also shifts. So there are three factors, depending on them the Q point shifts from its original position. These factors are leakage current, VBE, and beta factor. Okay, so with this I would like to conclude my topic. I hope you have understood, you got the concept of transistor biasing. Let me give a quick review of this. Let me go to the very first slide of this. Okay. So basically, transistor biasing is the requirement of applying DC voltage to a transistor, and then this DC voltage is applied so that the Q point is obtained at the middle of the load line. The load line can be drawn in two ways, AC and DC. To draw the load line, first of all we draw the circuit and remove AC source, then we apply KVL at the output port and draw the equation in the form of Y equal to Mx plus C. After the load line is drawn, we determine the factors, depending on them the Q point shifts, which is beta, VBE, and ICO. and to keep them fixed in its original position, the biasing is required. So this is what is required. Thank you so much.